Okay, see Lindelof videos, AP Calculus, approximating the area under a curve. And what we did in our last video is we did a left-hand sum. Now we're going to do a right-hand approximation. Going to start off with where we started and say that to approximate the area under a curve, let f of x be non-negative on a to b. And we're going to find the area of the region lying beneath the curve, so beneath this, but above the x-axis. And so let this be the x-axis if you don't mind. So let this be the x-axis, and we're looking for the area in between. There will be a time where it won't necessarily have to be above the x-axis, but that's where we are for now. We talked briefly about breaking our function into subintervals, and we said that in this case we're going to make even subintervals or equal subintervals, and to do that we just take the distance. So the distance is from a to b, so the total distance is b minus a would give us the total distance, divided by the number of subintervals that we have, and we'd get the base. Because remember, to find the area of a rectangle, right, the area equals base times height, and I'm saying to you that base is that. So this is the base, and the height is f of this thing. So we did our left-hand sums, and we got a low approximation, and we talked about the fact when we did, in this case, this left-hand sum, that we missed counting this area, this area, and this area, and this area, so our approximation was low. So what we're going to do now is we're going to do a right-hand sum to see if we can try to find a range of what our true area is. So I'm going to go back to this. So here's us setting up our right hand. So here's our right-hand sum, our right-hand approximation. So here's our right-hand approximation. If you look, this is exactly the same curve that we used before. X sub 0 is still equal to a, b is still equal to x sub 1, and I said that we are going to have equal subintervals. So I'm going to say that here's my subinterval here, so this distance, and then the same distance again, and then the same distance again, and this same distance again. And if you're willing to believe with me that this distance is also the same, that would be terrific. Thank you very much. And what we're going to do with this right-hand sum is this. We're going to draw this up straight up like this, right? Draw this up like, let me show you what's happening here. So let me make the first rectangle. The first rectangle will look like this. And you can see now, on the last one, look, we had an underestimate, right? We had a very low estimate because we left out all these areas. When we do our second one, we're going to get an overestimation. We're going to get an overestimation. I'm going to do the same thing here. I'm going to draw this straight up to here. You can see that this is a right-hand sum because the corner of our rectangle touches the right side of the right corner of our rectangle touches the curve, right? I'm going to go up there, and you can see that this is the approximate area, but we have a little bit too much. I'm going to do the same thing again here. I know that these bases don't look the same. Please forgive me and try to buy with me that it did work. And then we have this one. If you don't mind, I flattened my curve out too much. I should make it look a little steeper so you can actually see what's going on here. So I'll do that, if you don't mind, just to make it look better. But then I'm going to do the same thing and go straight up to here. And when I come over, you see that I overestimated by this area, right? So now we have to figure out, okay, well, how do we count these? We said, well, this point right here, a, is x sub 0. Well, that makes this x sub 1. This makes this x sub 2, x sub 3. We know this is x sub n. So the one before x sub n would be x sub n minus 1. And that's really important for the left-hand estimation. So let's see, as we add these things up, what do we have? So let's look for this area right here. So I'm not going to do them all, but let's look for this area right here. And I think that we can agree, because we talked about this a second ago, that its base, all the bases would be change of x. So the base is change of x. So we have the area of the first rectangle is f of, what's its height? Its height is f of x sub 1. It's this height right here, isn't it? So f of x sub 1, right, times its base, change of x. So far, so good? That gives us the first area. Then we'd look for the second area, and that would be f of x sub 2 times change of x plus f of x sub 3 times change in x right? And we would keep adding these rectangles. The reason I'm not going to add them all, we could here because this is exhaustive. That is that we could complete this. But what if we had 1,000 of these things? So let's just agree that we're going to add up all the areas until we get to the last one. And what is the height of the last rectangle? Well, the height of the last rectangle is f of x sub n. So we have f of x sub n times change in x. So the question is, what does all that give us? How do we turn this into sigma notation? Because that's what the trick is here. First, we have to figure out what it is we're doing. And once we have it defined, then we can really take a real shot at this. So I'm going to put this into sigma notation and say this is what my intention is. This says I'm going to add up all the areas, starting with f of x sub 1, right, times change of x. So we're going to go from I is equal to 1 to n. I is equal to 1 is the first one, is the first height. The last height is f of x sub n. F of x sub n, this is x sub n, and that's its height. So this makes it a lot cleaner. This and this are equivalent statements. So that's really what I wanted us to get to from here. Understanding this gets us to understanding this gets us a really good start on the Riemann sum, and that's going to really help us. So got to kind of follow this. Hopefully this was helpful to you. If you have any questions or comments, please let me know. And if you haven't already subscribed, please do. Thanks.